Greetings. So welcome to today's session. So let me begin today's class with a brief recap of what we were discussing today, and then we'll go forward, right? So if you recall, we were looking at the root locus, and the main what to say feature of the root locus is that like we would be able to obtain a graphical visualization, right, of the variation of the closed loop poles as we vary a system parameter, and consequently, we would be able to figure out, ranges of, let's say, design parameters for which we would be able to achieve both closed loop system stability and closed loop system performance. So that is the motivation behind looking at the root locus. So just to recap what we did yesterday, is that like first to begin with, we consider the open loop transfer function to be of the form k times s plus z1 till s plus zm divided by s plus p1 times s plus pn, and minus z1 through minus zm are the open loop 0, minus p1 through minus pn are the open loop poles. So then what happens is that the root locus traces the evolution of the closed loop poles with variation in the parameter k, and the root locus will have n branches of curves. Okay, so we can see that the order of the system is n, and so it will have n branches or curves. Okay, so there are some steps involved in the root locus. The first step is something we discussed. The first step is to locate the the open loop poles and the open loop zeros in the complex plane. And we saw that every branch of the root locus will start at an open loop pole as k tends to 0, and will either go to an open loop 0 as k tends to infinity, or it will go to infinity in the S plane as k tends to infinity along what is called asymptote. Okay, so let's get started with the second step, okay, in the construction of the root locus. And as we motivated step number 2, step number 2 has to do with how the root locus will start from a non-repeating open loop pole on the real axis. As we discussed yesterday, let's say we consider the open loop pole at -4. The root locus branches branch from -4 can start along any direction, right? But then we eliminated all directions other than those along the real axis by arguing that if the branch which starts from the pole at -4 goes into the complex plane, its mirror image should also be a branch, right? Because we are considering polynomials with real coefficients, and if we have a complex root, its conjugate also must be a root. So that eliminates the possibility of having the branch from a non-repeating open loop, such as open loop pole, such as that -4, from going into the complex plane directly, right? So we have only two possibilities. It can either go along the direction 1 or along the direction 2. Now the question is along which direction will it go? Okay, so this is where we use the angle condition. Okay, and we essentially look at how the portions on the real axis would lie on the root locus. So in order to do this, what we do is that we look at the real axis and then identify the regions, that are essentially present in the real axis and are segregated by the open loop poles and the open loop zeros. In this example, there are no open loop zeros, so we are considering only open loop poles. So we can observe that there are broadly 3 regions, okay, in the on the real axis. Okay, one region going from -infinity to -4, one region from -4 to 0, and one region from 0 to infinity. So if you look at the real axis, so let me draw the real axis alone here. Okay, if we consider only the real axis, right, we know that there are open loop poles at minus 4 and 0. So minus infinity to minus 4 is one region, minus 4 to 0 is another region, 0 to plus infinity is another region. Now the question becomes, which of these regions, lie on the root locus? So to answer that question, we are going to essentially ask ourselves, as to how the angle condition is satisfied. Okay, like by um, just what to say, by choosing test points. Okay, in these three regions. Please recall that when we started off with the discussion on root locus, we had two conditions, right? The angle condition and the magnitude condition, right? On the open loop transfer function. So if you recall, we wrote down the closed loop characteristic equation as d of h of s equal to -1. And that can be decomposed into two conditions, right? D of h of s magnitude is equal to 1. And the face of d of h of s is an odd multiple of 180 degrees. So these two conditions are obtained, and we are going to utilize the angle condition, okay, like in this particular the step, okay. So let's go to the document and then read the step, okay. Please note that the angle condition requires that if any value of x which satisfies the face of the open loop transfer function being an odd multiple of 180 degrees is lies on the root locus. Okay, so the keyword here is odd. Okay, it should be an odd multiple of 180 degrees. So now we can essentially look at this particular step. So step number 2 is to locate the root loci that lie on the real axis. So this is determined by the open loop poles and the open loop zeros that lie on the real axis. Okay, so that is important. So what we do is that we choose a test point on the real axis. If the total number of real open loop poles and real open loop zeros that lie to the right of this test point is odd, then that point lies on the root loop. Okay, so once again the key word here is odd. So what is the connection to our angle condition? Without going into the derivation, okay, of these steps, I am just giving the connection, okay, to you. So the connection is that we want an odd multiple of 180 degrees, right? Is it not? So that is why we are saying, hey, look, we choose a test point, and if we look to the right of the test point, and if we have the total number of real open loop poles and real open loop zeros to the right of the test point to be odd, then that point lies on the root locus. Okay, so the reason the word odd comes here because we need an odd multiple of 180 degrees, right? As far as our angle condition is concerned. So let's go back, okay, and then see what happens. Okay, so let us say we choose a test point, okay, ST1 here. Okay, this we are essentially looking in the region minus infinity to minus 4. Now we look to the right of this test point, and we count the number of real open loop zeros and the real open loop poles that lie to the right of this test point. We count -4 and -0. So we can count that there are two real open loop poles. Of course, there are no zeros at all, so, and no real open loop zeros here, right? So consequently, if we choose this test point between minus infinity and -4, and we look towards the right of this test point, we see that there is an even multiple, okay, or an even number of open loop poles and open loop zeros to its right. So this is not on the real root locus. Okay, so that's how we determine. Now, if we take another test point, the second test point between -4 and 0, right, and then we look to the right of it. Okay, and then we count the number of real open loop poles and real open loop zeros to the right. Now we can see that there is only one, right? The open loop pole at 0, okay, is the only real open loop pole there, and there is no open loop 0. So the total number is 1, okay, which lies to the right of this particular test point. So we can immediately observe that to the right of this test point ST2, which lies between -4 and 0, we have an odd multiple, right, of open loop poles and open loop zeros. Okay, so this lies on the root locus. Okay, so that's what we can interpret. Okay, so once again, if we look at the what to say the root locus, and that is, if we look at the test point ST2 and we look towards the right, we can immediately observe that there is a open loop pole at 0. Okay, and there are no real open loop zeros at all, right? So the total number of real open loop poles and open loop zeros to the right of ST2 is 1. So consequently, we can observe that this test point ST2, right, it does lie on the root locus, and consequently, this is what to say, the region -4 to 0 lies on the root locus. Okay, so 1 minute. There seems to be some issue with my pen. Just give me a second. So similarly, if we take a test point in the region of 0 to infinity, we could immediately observe that the number of real open loop poles to the right of the test point in the region 0 to infinity is 0, and there are no open loop zeros, right, to the right of it. Okay, so if you take a test point in the region from 0 to infinity, we can immediately observe that there are no real open loop poles and open loop zeros to the right of a test point, right, in the region 0 to infinity. So consequently, in the region 0 to infinity does not lie on the root locus. Okay, so we will consider as such. Okay, so let me write all these things down very clearly. So this lies on the root locus because, as we observe, the region from -4 to 0, right, has, if you take a test point, it has an odd number of real open loop poles and open loop zeros to the side. So similarly, if you take a test point ST3, okay, and we look to the right of it, right, in the real axis, so we see that there are no real open loop poles and no real open loop zeros. So the answer is 0. So this does not lie on the root locus. So as far as step 2 is concerned, the only part of the real axis that lies on the root locus is the region between -4 and 0. Sorry, I will call it -0. Okay, it's -4 and 0. Sorry about that. Okay. So I hope this step is clear. Once again, like I'm only giving a very intuitive explanation of all the steps. I'm not deriving logic behind every step. Okay, we are not going to be interested in the mathematical derivation as such, but rather, like we are going to argue very intuitively. Okay, as far as each step. All right. So please let me know if there are any questions. Now, let's go to the third step. Okay, so what is step number 3? Step number 3 is to determine what are called as asymptotes, okay, of the root locus. So, what do we mean by asymptotes? Asymptotes are the branches of the root locus when they go sufficiently far away, from the origin of the complex plane and towards infinity. Okay, so that's what we call as asymptotes. All right, and this step applies only when m is less than n. Okay, please note that a root locus will have n branches, right? And each branch will start from an open loop pole, right? There are n open loop poles, correct? And consequently, n closed loop poles. And if there are m open loop zeros, and if m is less than n, out of the n branches, m branches will terminate at an open loop zero. The remaining n minus m branches will go to infinity along the asymptote. So in the example that we are doing, the value of n is 2 and the value of m is 0, right? So certainly we are going to have asymptotes. Okay, so the logic behind this, okay, once again, like I'm only going to argue the reason. So the logic behind this is that, like, if the text point is chosen very far away from the origin, okay, then we can see that the angle contribution of each open loop pole cancels with that of an open loop zero. Okay, so essentially, let's say we argue like this. So suppose, like we have a case. Okay, let me draw a very simple schematic and explain it to you. So suppose I draw the complex plane. Okay, and I consider a scenario wherein, let us say I have an open loop pole at minus P1 and open loop 0 at minus Z1. Okay, suppose I take a test point which is very, very far away. Imagine that this FT is very far away from the origin. Okay, although in this figure I am drawing it very close by. Okay, so suppose I draw vectors from each open loop 0 and open loop pole to this test point ST. Let's say we call this angle as some theta 1, this angle as some phi 1. Okay. Now, if you take a look at angle of S plus Z1 divided by S plus P1, you just take these two factors, which is going to be angle of S plus Z1 minus angle of S plus P1. Okay, that's how complex algebra works. Okay, so if you take the ratio of two complex numbers, the phase is going to be the difference between the individual phases. Okay, so that's how we are going to do things. So now imagine that this ST goes to infinity. Okay, farther and farther away from the origin, right? So what will happen? We can see that theta 1 and phi 1 will almost become equal, right? So I'm sure all of us can appreciate the fact, and that is the reason why we say that as we what to say, go further and further, like from the origin, the angle contribution, right, from each open loop pole is going to cancel off with angle contribution from each open loop zero. Okay, so that is the reason behind this statement. So if at all there are asymptotes, okay, they are going to be straight lines which make an angle with the positive real axis of plus or minus 180 degrees times 2k plus 1 divided by n minus 1. So how did we get this? The denominator n minus m comes in because there are n minus m asymptotes. Okay, and the angle condition comes in because the numerator comes in plus or minus 180 degrees times 2k plus 1 comes in because that's the right hand side of the angle condition. All right. So as a result, please note that in general, okay, there will be n minus m asymptote. Okay. So step 3, as far as asymptotes is concerned, it applies only when m is less than n. Okay, so if m is equal to n, then there are no asymptotes. Okay, so please note that step 3 is valid only when m is less than n. All right, so that's what happens. So just to give a flavor of why we get this formula, if we consider the general structure of the open loop transfer function that we are dealing with, which will be k times s plus z1 till s plus zm divided by s plus p1 all the way till s plus pn, right? So if we are taking the phase of this factor, so we will immediately see that this is going to be the sum of the phases, in the numerator, okay, minus the sum of the phases in the denominator. Okay, so as we know, the phase of k is 0. Why? Because k is a positive real number, so the phase of k is 0, and as we go towards infinity, all these phases, let's say, they tend towards some theta. Okay, let's call this theta a. Okay, theta a indicates the angle made by the asymptote. Okay, and this should be an odd multiple of 180 degrees, right? So that's the angle condition. So now we can immediately see that on the right hand side, we are going to have n minus m times theta a, of course, minus of n minus m, but then you can take the minus sign to the other side. It will still remain plus or minus 180 degrees times 2k plus 1 will be the angle condition, equation from the angle condition. So the angle made by the asymptote with the positive real axis will be plus or minus 180 degrees times 2k plus 1 divided by n minus. Okay, so I hope it is clear how we got this formula. So I just done a sample derivation. Okay, so to just show you how we get the angle made by the asymptote. Okay, the formula for the angle made by the asymptote. Okay, so this is the angle made by asymptote. Okay, once again, please note that there are n minus m asymptotes, and the notion of asymptote is valid only when m is less than n. Okay, otherwise it is not valid. Okay, so when m is equal to n, there are no asymptotes. So in our problem, okay, the current problem, n is equal to 2, m is equal to 0. So this implies that angle made by the asymptote theta a is going to be equal to plus or minus 180 degrees times 2k plus 1 divided by 2, okay, which is going to be plus or minus 90 degrees, right, times 2k plus 1. Okay, k is equal to 0, 1, 2, and so on. Okay, so this can be taken as either plus 90 degrees or minus 90 degrees, okay, because there are two asymptotes, or we can say it is 90 degrees and 270 degrees. Okay, so that's how we can. All right, so I will show you what these angles mean shortly. Okay, please give me a minute, and then I will show you how to plot these angles. Okay, in the S plane, so that like we can locate the asymptote. All right, so that's the notion of asymptote. Now, going ahead, there is another step, right, in this particular step. That is the point of intersection of the asymptote. So, what is this point of intersection of the asymptote? How do we find this? You know, it so happens that all the asymptotes will meet at a common point on the real axis, and that point is given by this formula. That is, what we do is that like we take all the sum of all the open loop poles and subtract the sum of open loop zeros and divide by n minus m. Okay, so that's the point of intersection of the asymptote. All right. In this particular problem, we will calculate what is the corresponding point of intersection of the asymptote. So consequently, the point of intersection in this particular problem, there are two asymptotes. The point of intersection of the asymptotes is going to be equal to the sum of the open loop poles, right? So the open loop poles are 0 and minus 4, minus the sum of the open loop zeros, there are nil, divided by n minus 1, which is 2 minus 0. So the answer is minus 2. So minus 2 is the point of intersection of the two asymptotes, okay, as far as this particular problem is concerned. So what have we done in this step? We have essentially tried to figure out, what are the asymptotes in the case when m is less than n, and we have essentially tried to find what would be the angle made by the asymptote and what will be the corresponding point of intersection of the asymptote. All right. So going back to this general curve, so if I want to plot the asymptotes, so what will happen is that like the asymptotes intersect at -2. So this is the point of intersection of the asymptote. So one asymptote is going to be vertically up, right? So that will be the asymptote going at plus 90 degrees. Another asymptote will be vertically downwards, right? In this particular problem, right? So this will be the two asymptotes. So this is asymptote 1, okay, and this is asymptote 2. Okay, so you can see that this is, we can say this is plus 90 degrees and this is minus 90 degrees because the angle convention negative clockwise, or one can say it's also 270 degrees, right? So that's why both are equivalent. Okay, writing minus 90 degrees and 270 degrees would be equivalent. Okay, so we can see that in this particular problem, these are the two assumptions. All right. Okay. So okay, any questions on this step? As far as step 3 is concerned. All right. Okay. So now let's go to the next step. Okay. So we have figured out what are the asymptotes, how many asymptotes are there, and how to construct the asymptotes. Right. So given this, let's go to step 4, which deals with what are called as breakaway or break-in points. So what are these breakaway or break-in points? So let me explain. By plotting the S-line for our particular example. So if we plot the two open loop poles, okay, in our particular example, one branch from -4 will start like this, another branch from 0 will start like this. How can I be sure that this is how the branch from -4 and 0 will start? See, we know that one branch starts from -4, right? And we also argued that it has to go along the real axis. But it can go either to the right or to the left. How did I ensure that now it goes only to the right?
From step 2.
From
step 2.
From step 2. Very good. What was step 2? We essentially located the paths of the real axis on the root locus, right? And we figured that -4 to 0 only lies on the root locus, not -infinity to -4 and not 0 to infinity. So I cannot have the root locus going like this, right? That is not possible, right? Neither can I have this branch from 0 starting with this, right? Both are not possible. So by elimination, this is the only way. All right. So I hope that is clear. So let me remove these so that we can avoid confusion. Okay. Yeah. So I hope this is clear how we got these two branches to come. So now we can see that at some point these two branches are going to come towards each other. They are going to hit each other, and then they are going to essentially go out, okay, into the complex plane. Okay, such a point, okay, is what is called as a breakaway point. Okay, so a breakaway point is a point, for example, when you have two open loop poles on the real axis like this, and then two branches of the root locus start from each open loop pole. They essentially intersect each other, and then they go away, right? So that's what is called as a breakaway point. Okay, so now the question is, like how do we find out, like such breakaway points to begin with? Okay, so in this regard, we are going to use some results from complex algebra. But before that, let's go and read the step 4. Okay, so the same analysis or the step applies to what are called break-in points. So what is a break-in point? We can have two branches coming from the complex plane, hitting a common point on the real axis and going to real open loop. Okay, I will draw a scenario shortly. But this step is common for the breakaway and break-in point. Okay, so what we do is the following. Okay, we use this equation, okay, to solve for breakaway and break-in point. But the question becomes, how do we get this equation in the first place? Okay, so let's look at that. So now we recall that the closed loop characteristic equation can be written in this form, right? So it is 1 plus g of s h of s equals 0, and g of s h of s we write as k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pi. Okay, and this is equal to 0. This is g of s h of s. All right. So what we do is that let's call this factor s plus z1 to s plus zm to be a of s. Okay, and s plus p1 through s plus pn as some b of s. Okay. Let's say that is what we have. Then what we have is that like this equation takes the form 1 plus k times a of s divided by b of s equal to 0. So this is just for simplicity, right? So what we are writing as a polynomial capital A of s is that s plus z1 till s plus zn, or we are writing s plus p1 through s plus pn as the polynomial capital B of s. Okay, so that's what we are doing. So consequently, the closed loop characteristic equation can be written as 1 plus k times A of s divided by B of s. All right. So once we have this in this form, we process it. Okay, but before we process, like I just wanted to give you an example, so that like we can understand, right? So let's consider an example. Multiplied by s plus 2, right? What is the order of this polynomial? Third order, right? So, yeah. So, and what are the roots of this polynomial? So, if we solve for this,
-1, -1, -2.
so we have -1, -1, and -2. So, immediately we can see that the root -1 repeats twice. Okay, that's what is called as multiplicity. So, the multiplicity of -1, the root at -1 is 2. Okay, so it repeats. So how do we find, okay, if there is a repeating root? Why are we worried about this repeating root suddenly? Because let us say, suppose there is a breakaway point, right, at which two branches of the root locus intersect each other. Then we see that there is a repeating root at the repeating closed loop pole at the breakaway point. Is it not? Because please remember, each branch of the root locus corresponds to one closed loop pole, right? So if there is a scenario where two branches hit each other, okay, then that means that at that point there is a repeating pole, right? And that's what we need to focus upon, and that's why this multiplicity becomes important. All right. So now, if we have the multiplicity of the root at -1 to be 2, and we take we want to formalize the process. Let's say we take the first derivative of d of s with respect to s. D prime s means we are taking the first derivative of uh, the polynomial d of s with s. So immediately we can see that we'll get 2 times s plus 1 times s plus 2 plus s plus 1 whole square. All right. So we immediately notice one thing, right? So from here, if we evaluate the derivative at s equals -1, what do we get? If we substitute s equals -1 in the derivative, first derivative, what do we get?
0.
Zero.
Right? Yeah. If we evaluate the derivative at s equals -2, what do we get?
1.
We get 1. So essentially, what happens is that if we essentially have a repeating root, see, in general, okay, if you consider any polynomial, any root of the polynomial will make the polynomial to be 0, right? That's the definition of the root. On the other hand, if you have a repeating root, what's going to happen is that not only will it make the polynomial to be 0, it will also, if the multiplicity is 2, the first derivative also will be 0, right? So that is the fact which we are going to use to our advantage. So given this fact, what we do is the following, right? We differentiate this 1 plus k a of s divided by b of s, and we take the derivative. So if we take the derivative of this, we are going to get k times one derivative of 1 is 0, and we use the what to say p by q rule of differentiation. Okay, so essentially we'll have b of s whole squared, then we'll have a prime s b of s minus a of s b prime s, right, is equal to 0. Okay, so this implies that, of course, if there is a repeating root or a breakaway point, what we need to have is that, like, we need to have just changing the sign. We can have what to say, a prime s, sorry, equating it to 0. We can have a prime s b of s minus a of s b prime s to be equal to. Okay, so this is the condition. All right. So for testing for a repeating root. So consequently, we can immediately observe, that this is how the breakaway point or break-in point is evaluated, right? So we can immediately see that that's the same equation. Of course, we have just switched the order of the terms, but that's okay, because you take the terms to the other side of the equation, right? So you'll get b prime s times a of s minus a prime s times b of s equal to 0. Okay, so we need to do this. So let's apply for our problem. In our problem, what happens is that here a of s is 1. Okay, because if you look at our open loop transfer function, a of s is 1. B of s is going to be equal to s times s plus 4, right? Which is nothing but s squared plus 4s. So this implies that a prime s is going to be, what will be a prime s? How did I get this? Please note that in our problem, g of s h of s is k divided by s times s plus 4, right? So if we map it to k times a of s by b of s, a of s becomes 1, right? So that's how we do it. Okay, and b of s becomes s squared plus 4. So what will be a prime s? If you take the derivative of 1 with respect to s, what will we have? You'll have 0, right? Because it's a constant term, right? And what will be the derivative of b of s with respect to s?
2s plus 4.
We'll have 2s plus 4, right? So this is what we have. So consequently, what we have is the following. The equation a prime s b of s minus b of s, or even if you write it the other way around, right? B prime s a of s minus a prime s b of s equal to 0 will imply that b prime s is 2s plus 4. A of s is 1. Okay, a prime s is 0. This becomes 0. 0 times s squared plus 4s is equal to 0. So this will give us 2s plus 4 equal to 0. So this will be, if we solve this, we'll get a potential breakaway point at minus 2. Okay, why do I call it as a potential breakaway point? It is only a possibility. We have to do one more check, okay, which I will explain shortly, because we need to check the value of k, okay, at this solution. Okay, how do we check the value of k? Because when we started our analysis, we have started our steps for k being positive real number, right? So we have to ensure that whatever solution we get, for a potential breakaway point, there should also be positive. Okay, otherwise it is not a breakaway point. So we have to evaluate minus b of s divided by a of s at this is b equals minus 2. So what do you think will the answer be if we do this? So what will be this ratio, s squared plus 4s divided by 1? This will be equal to
4, sir.
4. Okay. So we can see that this is a positive number, right? Is it not? Okay. So consequently, this is a breakaway point. Okay. So consequently, S equal to -2 is a breakaway point at which K is equal to 4. All right. Okay. So consequently, this is how we find breakaway and break-in points, right? So one can note something interesting, which is very specific for this example, not true in general. It so turns out that the breakaway point is at -2, and we also saw that the point of intersection of the asymptote was also at -2. Okay, so this is a special case. Okay, in general, it is not true. Okay, that is. In this specific example, the point of intersection of the asymptote and the breakaway point happens to be at both happen to be at -2. Okay, but that's not necessarily true in general. Okay, so that's something we need to remember. All right. Okay. So now the question is, what is this break-in point? So what is this break-in point? We looked at a breakaway point. Now, what is this break-in point? So a break-in point, I'm just giving an example. Let us say we had two open loop zeros, okay, at these two locations. Then what may happen is that, like, we may have two branches coming in like this, sorry. Okay, one branch coming in like this, one branch coming in like this. They may intersect on the real axis, and the two branches may go and terminate at an open loop. Okay, then we have what is called as a break-in point. So I hope now the meaning of the term is clear, right? A breakaway point means the root locus branches break away from the real axis. A break-in point means the root locus branches break into the axis. Okay, so that is the subtle difference. But the step is the same. That is, we evaluate the roots corresponding to b prime as a of s minus a prime as b of s equal to 0. And then, like, we calculate the solution, and then, like, we essentially look at the value of k corresponding to the solutions that we get, and whatever value of s that gives a positive k is the correct breakaway or break-in point. Okay. So that concludes step number 4. Okay, so which is on breakaway and break-in point. All right. So any questions on steps 2, 3, 4 that we have discussed? Okay. So if not, let me close this lecture, and then we'll continue from here in the next